believe they were all here. They were here a minute ago before I sent them for coffee. Nope. Guess not. Is everybody ready? What's going on? That's 1 yes, 2 yes, 3 yes. Okay, we're going to get rolling. Jennifer was just in. She just came through, so time to get to getting. I'm going to share the screen. Let's get this rolling. All right. All right, so this is module 1, ENSA, single area OSPF V2. If you have questions, holler them out or shoot a text. I'll try to keep my eye on the text, okay? It's usually in the way, so I back screen it. Anyway, you should be able to describe basic OSPF features and characteristics, describe the OSPF packet types used in single area OSPF, explain how single area OSPF operates. It's important to understand the packet types and how OSPF operates, okay? That's a critical feature. Can everybody still see that screen share? Somebody hit me with a yes in the text. Okay. I stopped the video just for the hell of it. Anyway, the features and characteristics of OSPF. OSPF, link state routing protocol. Actually, it was built off of an earlier version of ISIS. Purely link state, hierarchical protocol. That means that your addressing must also be hierarchical in order for OSPF to operate in an efficient manner, okay? Developed as an alternative for the distance vector RIP protocol, routing information protocol. If you remember, RIP is distance vector. It's purely based on hop count. In other words, distance, how many hops, vector, out which interface. OSPF has significant advantages over RIP in that it offers faster convergence, scales to much larger network implementations. Now, as a hierarchical routing protocol, OSPF is based on the concept of areas. Area 0 is the transit area, okay? It is the area that all non-zero areas must transit to get to other non-zero areas. Traffic in area 1 connected directly to area 51 via a link can never go from 1 to 51 unless it goes 1 to 0 to 51, okay? So area 0 is the main area. It's the transit area, okay? Now, that doesn't mean that you can't go from 1 to 51. As long as you can get to area 0, you can create a virtual link. That's a conversation for a later time, okay? It's not important right now. Right now, you need to understand, by default, no traffic goes from a non-zero area to a non-zero area without first crossing area 0, the transit area, okay? So, significant advantages over RIP, offers faster convergence and scales to much larger network implementations. RIP has a maximum diameter of 15 hops. The 16th hop is always unreachable to RIP, whereas OSPF can have as many as 50. We recommend no more than 50 routers in an area. Doesn't matter if it's area 0, area 1, area 2, 10, 50, 100. Doesn't matter. No more than 50 routers per area. Now, when you think about that, that's like on a scale of magnitudes of what RIP is capable of, okay? So really huge networks, service providers and large corporations like OSPF. But remember, your routing protocol, your choice of routing protocol is always going to be based on the available technical skill. Okay? You know, you have people that like EIGRP, people that like OSPF, people that like ISIS. So keep that in mind. Okay? OSPF is a purely link state routing protocol, uses the concept of areas. A network administrator can divide the routing domain into distinct areas that help control routing update traffic. Now realize, all routing updates in Area 1 remain in Area 1. And then at the ABR, you can configure as to what type information you want to propagate from Area 1 into Area 0. Now, if you designed your network hierarchically, addressing and everything, you'd be able to send a single summary route into Area 0, and then Area 0 could propagate that single summary route into other areas. Or you can send all of the routes in an area through Area 0 to other areas, okay? A link is simply an interface on a router, okay? A network segment that connects two routers, or a stub network, such as an Ethernet LAN connected to a single router. Information about the state of a link is known as a link state. All link state information includes the network prefix, prefix length, and the cost to reach that link. Module covers basic single area OSPF implementations and configurations. So very simplistically, it covers OSPF. Trust me, OSPF can get very twisted very quickly. It is a complex protocol, and if you know how to configure it, you can make a network hum with OSPF. OSPF gets a bad rap a lot of times because it's resource intensive. It's only resource intensive if you didn't do your job and configure it correctly. Other than that, other protocols send out update messages RIP every 30 seconds. OSPF only sends little hello packets every 10 seconds by default. Okay, not routing updates, little hello packets. Every 30 minutes if nothing changed in the network. Nothing, I mean, no links went down, nothing changed. OSPF every 30 minutes will send an all SPF packet that only requires a simple acknowledgement. In other words, yeah, I got it, but nothing changed, okay? All routing protocols share similar components. They all use routing protocol messages to exchange route information. The messages help build data structures, which are processed and used by a routing algorithm to calculate the best route to every destination. Routers running OSPF exchange messages to convey routing information using 5 types of packets. You have hello packets, database description packets. You'll see these in short form as DD, database description, DBD, database description, okay, and DDP, database description packet. They all mean the same thing. DD, DBD, DDP, all the same packet type, database description packet. Then you have link state requests. Those are LSRs. Link state updates, LSUs. Remember, that's what's contained inside of an LSU is various other OSPF packet types. And then you have link state acknowledgement packets. Remember, always with every single protocol, hello packets are never acknowledged, okay? However, database description packets, link state requests, link state update, those are all acknowledged. Hellos are never acknowledged. Hellos are utilized to reset timers. That's why they're such small packets, because they're only used really to reset timers and convey various small pieces of information that routers need in order to route between each other, okay? Packets are used to discover neighboring routers, also exchange routing information and maintain accurate information about the network. Elaborate what sub-network and pocket network? What? Where'd you get sub-network?
No, I mean stub network. typo. And
Stub
Pocket
network.
Network.
Pocket network.
Right. It's a I had to Google Stub Network, and it says the same as Pocket Network. When you go back a slide about
Well,
internet net,
here. All right. So here, where are we?
third line.
Third line. Not the third line.
I mean, not third line, third statement, third bullet point.
One,
Where it
two,
says,
three.
where it says a link is an interface. So my
Yeah, a
question.
stub network. Let me put up a whiteboard and draw a stub network for you. Okay.
Thank you.
All right. All right, so a stub network essentially looks like this. You have a router. That router is connected to other routers. All right. And then you have a router down here that has networks, whatever. You have a LAN here, right? Now, if you look at this stub router, there's only one way in and one way out. Okay, so this router, you see the mouse, right? This router can use a quad 0 to get everywhere else. He has no neighbors. There's only one way in to the address block behind and one way out to everything else. So this router can use a static route to reach this network, and this router can use a quad 0 to reach every other network. Now, these routers here have redundant alternate pathways. Okay, they're not stub routers. They actually connect to other devices elsewhere.
Thank you. That was very clear.
Okay, does that make sense?
Yes, it makes sense now. Thank you.
This is a stub network. Pocket network. I have never heard it called a pocket network, but stub network, absolutely, we use that term all the time.
Okay. Okay. Thank you.
All right. Okay, let's get back to the other share. Oh man, I lost it. There it is. All right, so let me just run this forward to where we were. All right, now there are various types of packets. Remember that these 5 packet types you must know. Hello, database description packet, link state request packets, link state update packets, link state acknowledgements. Hellos, DBDs, DDPs, DDs, LSRs, LSUs, LSACs. Okay. Hello packets are never acknowledged. They're only used to reset various timers. When you look at it, OSPF uses 3 types of tables. It uses an adjacency database, which we now call a neighbor table. It uses a link state database, LSDB, which we now call a topology table. It uses a forwarding database, which has always been called the forwarding database or routing table. Okay? The routing table is what you see when you type show IP route. The link state database will be identical for all routers within a given area, like area 1. All routers in area 1 will have an identical link state database. However, each router will calculate a unique route to deposit in the routing table because it's based on their perspective of how to reach a given network. Even though the link state database is identical, each router calculates a unique route to reach a destination. The adjacency database, the neighbor table, is simply a list of all neighboring routers to which a router has established bidirectional communication. That table is also unique for each router because every router has different interfaces connected to different other devices and networks. Links. can be viewed using the show IP OSPF neighbor command. Okay, that'll show you a list of all neighboring router IDs, as well as the interface address and various other information. Show IP OSPF database gives you a read on an area by area basis of every route learned and the different types of routes that they are, because there are different types of routes. Okay, the routing table, if you type show IP route for OSPF, you'll see a couple of different route types depending on the configuration of OSPF. You may see O's. Those are routes internal to an area, like Area 1. Everything in Area 1 on an Area 1 router will show as an O, meaning OSPF intra area, internal to the area. Anything that crosses an ABR is going to show as an OIA, inter area. That means from Area 1 into Area 0 or Area 0 into Area 1. Those routes are not native to the area. They come from other areas. Then you have ON1s, ON2s. Those are not so stubby area. We don't cover NSSA in this class, so you don't have to worry about those. However, there is one rule, and that's with the ones are cumulative cost, the twos are static cost, okay? Now, by default, ASBRs, Autonomous System Boundary Routers, generate type 2 metrics for anything brought into OSPF. And then you have OE1, OE2. You'll be more familiar with the OE1s and OE2s because that's what you see commonly. Unless you're running not so stubby areas like that, then your routes will show as OE1s or OE2s. That means OSPF external type 1 or OSPF external type 2. Remember, I told you the twos are a static cost. If it comes into OSPF on router R1 with a cost of 20, when that route reaches going through router 2, 3, 5, 10, when it reaches router 20, since it was imported into OSPF as an OSPF external type 2 by default on the ASBR, at router 20, the cost for the link will still be 20. It won't change because it's a static cost. However, if you instruct the ASBR to import external routes as metric type 1 using the metric -type number 1 command in the routing protocol, then when it gets to router 20, it will not have a cost of 20. The cost will be very different. And excuse me, that's my cat having a sneezing fit. Don't worry, she'll choke up a snot. There it goes. She's nasty. She snots the whole place out. Got to mop up after her. Anyway, like I said, the ones, whether it's N1 or E1, are cumulative cost. That means every link in the path is added to the cost that the link was brought in as. The twos are a static cost. Doesn't matter if it's N2 or E2, they're static. They stay what they are when they came in. 50 routers away, it's the same cost. Now, you would want to convert to type 1 if you have more than one exit point for the network. In other words, if you have two ASBRs that have two separate links to external networks, you would want to use the lowest cost path to leave the network. Okay? So you would convert to a metric type 1 on the ASBRs. This way, both links brought in to OSPF from different ASBRs with different connection points to external networks would then accumulate cost so that deep down in your network, you know which is the better cost to get out of the network to a given network, subnetwork, destination. Okay? So anyway, what? Question? Link state database, topology table, is a lists all the information about all other routers in the network Database represents the network link state database, the state of all links in the network. Okay. OSPF has comprehensive knowledge of the network within its area, a given area. All routers within an area will have an identical link state database. You can view this using the show IP OSPF database command. The routing table you're already familiar with, simply a list of routes generated when an algorithm is run on the link state database. Each router's routing table is unique, even though they calculate the same link state database on all routers in an area. Each router will have a unique cost to reach each destination. Okay, contains information on how and where to send packets to other routers, can be viewed using the show IP route command. Components of OSPF, the router builds the topology table, the link state database, using results of calculations based on the Dijkstra is how it's pronounced, shortest path first algorithm, SPF algorithm. The SPF algorithm is based on a cumulative cost to reach a destination. The SPF, now cumulative cost based on bandwidth calculation, okay? The SPF algorithm creates a shortest path first tree by placing each router at the root of the tree and calculating the shortest path to each node. Now, node can be router, can be host. Network in this case is what we're looking at, because OSPF calculates the lowest cost path to reach each network. And then OSPF places the best routes into the forwarding database, which is used to make the routing table. To maintain the routing information, OSPF routers complete a generic link state routing process to reach a state of convergence. Convergence simply means when all routers are operating with the same link/state knowledge base. That sentence has nothing to do with link state routing, okay? That same statement holds true for EIGRP, RIP, ISIS, BGP, okay? It just means that all routers within a routing domain have come to an agreement on what the network looks like. In other words, everybody's stable and everybody knows how to get everywhere, okay? That's convergence. The following are link state routing steps that are completed by a router. First, you establish neighbor adjacencies using hello packets. Exchange link state advertisements using database description packets, link state requests, link state updates, and link state acknowledgements. Build the link state database. Execute the shortest path first algorithm. That means run the Dijkstra algorithm on the link state database. Choose the best route to deposit in the IP routing table. To make OSPF more efficient and scalable, OSPF supports hierarchical routing using areas. An OSPF area is a group of routers that share the same link state information in their link state databases. OSPF can be implemented in one of two ways as follows. Single area OSPF. All routers are in one area. The best practice in this case is to use area 0 as your area ID. Okay? Now with single area OSPF, remember, you're pretty much limited to about 50 routers in the area. And much more than that, and the protocol itself will cause all the devices to come to their knees in terms of resource utilization. Okay? Multi-area OSPF. OSPF is implemented using multiple areas in a hierarchical fashion. All areas have to connect to the backbone area, the transit area, area 0. Routers interconnecting the areas are referred to as area border routers. Now, there are a couple of different router types in OSPF. You have ABRs, area border routers, will have an interface or more, one or more, at least one though, or more interfaces connected to area 0. And then one or more interfaces connected to another area or different areas. You know, a router in OSPF can have two interfaces in area 0, one interface in area 1, 3 interfaces in area 3. Okay, it depends on the model. How big is the box? How many layer 3 interfaces do you have? And what is the routing goal? Okay. Okay, anyway. You have internal routers. Internal routers means all interfaces, all network statements in that router are of the same area ID. So all area 1 or all area 0 would be an internal router. And ABR is a router that has one or more interfaces in area 0 and one or more interfaces in another area or other areas. An ASBR, Autonomous System Boundary Router, will have at least one interface connected to a non-OSPF routing domain. That means simply the internet or another routing protocol like EIGRP. That would make that device an autonomous system boundary router. Okay, you have backbone routers. These are routers that have interfaces in area 0. And then on multi-access networks like Ethernet, you have designated routers, backup designated routers. So there are a couple of terms that you need to be familiar with OSPF and remember them, because you're going to see it every day that you work with OSPF. Okay. Anyway, this module focuses on single area OSPF v2. They're making it easy on you. My choice is multi-area, but multi-area OSPF. Hierarchical topology design options with multi-area OSPF can offer the following advantages. Within each area, you'll have smaller routing tables. Tables are smaller because there are fewer routing table entries. This is because network addresses can be summarized at ABRs between the areas. However, remember that route summarization in OSPF is not enabled by default in OSPF. It is a manual task using the area range command or the IP OSPF summary address command. Reduced link state update overhead. Designing multi-area OSPF with smaller areas minimizes processing and memory requirements. Because remember, the router only has to deal with what is in its area and whatever summary route came across the ABR. That makes routing tables smaller within an area because all they need to know is what is the path to the ABR to get to the other networks. Rather than all of the individual paths, it's one summary path. Okay? Reduce frequency of shortest path first calculations. Multi-area OSPF localizes the impact of a topology change within the area. For instance, it minimizes the routing update impact because the LSA, link state advertisement flooding, stops at the ABR. So if you look at the diagram there, if you're looking at area 51, you see the X on that link. Only area 51 routers have to recalculate to compensate for that outage. Area 0 never even knows the outage happened. Neither does area 1. So they don't have to recalculate their routing tables and send new updates and all that good stuff. Area 51 handles it internally at R2, which is the ABR, area border router. So only network statements with area 51 on them have to deal with that outage. The area 0 never sees it. Area 1 never sees it. Let's work on the protocol overall in other areas. OSPF v3 is the OSPF v2 equivalent for exchanging IPv6 prefixes. OSPF v3 exchanges routing information to populate the IPv6 routing table with remote prefixes. With the OSPF v3 address families feature, OSPF v3 includes support for both IPv4 and IPv6. OSPF address families well beyond the scope of this curriculum, okay? Now, OSPF v3 can be configured two ways. In the legacy way, as well as in the address family method. The differences are this. With OSPF v3 in the legacy manner, you would type IPv6 router OSPF, give it a process ID, set your router ID, your auto command, the auto cost reference bandwidth command if you have interfaces greater than 100 megabit. And then you would go to the interface like int G0/0 and type IPv6 OSPF process 10 area, whatever area you want that interface to be routed into. Now, or for is a more appropriate phrase. Now, for OSPF pure, OSPF v3, the modern method, you would type simply in global config, router OSPF v3, press enter. You would create an address family for IPv4, a topology base for IPv4, an address family for IPv6, and a topology base for IPv6. Now, everything is configured locally. You don't have to go back and forth between the protocol and the interface to tweak various timers and other configuration parameters. Everything is done in the address family and topology base. Whereas with OSPF, the legacy configuration for OSPF, if you want to tweak the interface timers, you got to go to the interface and do that. Okay? So it localizes the configuration to the address family mode. All right? So OSPF v3, same functionality as OSPF v2, but it uses IPv6 as the network layer transport, communicating with OSPF v3 peers, advertising IPv6 routes. OSPF v3 also uses the shortest path first algorithm, Dijkstra algorithm, as the computation engine to determine the best paths throughout the routing domain. OSPF v3 has separate processes from its IPv4 counterpart. Processes and operations basically the same as in the IPv4 routing protocol, but run independently. Now, what that means is that if you're routing OSPF v2 for IPv4 and you have dual stacked interfaces and you're running IPv6 also, and you're routing OSPF for IPv6, okay, you will have two neighbor tables, two link state databases, and two routing tables, one for IPv4, one for IPv6 for every part of the process. That means that you would type show IP OSPF neighbor to see the IPv4 neighbor table, show IPv6 OSPF neighbor to see the IPv6 neighbor table, show IP OSPF database to see the IPv4 database, show IPv6 OSPF database to see the IPv6 link state database or topology table, either way you want to go. Show IP route to see the IPv4 routes, show IPv6 route to see the IPv6 routes. So they run totally separate resources. And do note, you can use the same process ID for IPv4 as IPv6. So if you type router OSPF 10, that's your process ID. Okay? You can type IPv6 OSPF, IPv6 router OSPF 10 and run the same process ID for your IPv6. Why? Because they're two separate protocol stacks, an IPv4 protocol stack and IPv6 protocol stack. One has nothing to do with the other. That's why they each maintain their own set of tables. 3 tables in total: neighbor table, topology table, or link state adjacency database or neighbor table, link state database or topology table, forwarding database or routing table. Okay, they all mean the same thing. The packets themselves. In the diagram, you see you got hello, database description packets, link state requests, link state updates, and link state acknowledgements. They are respectively type 1, 2, 3, 4, and 5. You need to know type 1 is a hello. Type 2 is a DBD. Type 3 is an LSR. Type 4 is an LSU. And type 5 is an LSAC. The hello packets discover neighbors, build adjacencies between them. So certain information in the hello packet must match on neighboring routers in order to form a neighbor adjacency. The hello and dead interval must match at each end of a given link or wire in order for the two routers to establish a neighbor adjacency. Another thing that must match is the area ID. You cannot have an interface at one end of a wire in area 1 and an interface at the other end of the wire in area 0. Okay? Has to be the same network type. In other words, broadcast, non-broadcast, etc. We'll get into those commands later in the next chapter when you actually have to configure a network as an IP OSPF broadcast network. All right? And the address block must match or at least overlap by a really wide margin. Okay? Type 2 is a database description packet. This checks for database synchronization between routers. And LSR type 3 to request specific pieces of a link state database from router to router when you see somebody has information you do not currently have. A link state update is used to send specifically requested link state records. And then link state acknowledgement acknowledges all the other OSPF packet types except hello packets. Hello packets are never acknowledged. Doesn't matter what the protocol is, okay? They're never acknowledged, hello packets. They simply maintain timers. Link state updates also used to forward the OSPF routing updates. An LSU packet can contain 11 different types of OSPF v2 LSAs, link state advertisements. It also contains 2 additional LSAs. LSU and LSA often used interchangeably, but the correct hierarchy is the link state update packet contains the link state advertisement message. Okay? So here on the top, you see the LSU, type 4, which then contains various types of LSA. There are actually 11 LSAs. 9, 10, and 11 are considered the opaque LSAs. You do not have to know those. We don't cover those in CCNA, CCNP. Those are strictly CCIE topics because they're used for traffic engineering. However, it's nice to know that 9, 10, and 11 actually exist and that they are called the opaque LSAs used strictly for traffic engineering. Okay? So you got type 1 is simply a router LSA. Type 2 checks for database synchronization between routers. Now realize this type 1, type 2, 3 or 4, 5, 6, 7, 8 would be contained inside of a type 4 link state update. Okay? Type 3 or 4 are simply summary LSAs. Type 5, autonomous system external LSAs. These are routes brought into OSPF from an external source like default information originate or redistribute. Type 6, multicast OSPF LSAs. You'll see that also as MOP, M-O-P, multicast OSPF. 7 is defined for NSSA, not so stubby areas. You really don't have to know those. And 8 is the external attributes LSA for BGP. Border Gateway Protocol, not patrol. Some people need to learn how to type. It's not my picture. Anyway, the OSPF type 1 packet is the hello packets used to perform the following tasks. Discover OSPF neighbors and establish neighbor adjacencies. Advertise parameters on which 2 routers must agree in order to become neighbors. If the hello and dead interval is not the same at opposite ends of the wire, those routers will never talk to each other, never, okay? Elect a designated router and a backup designated router on all multi-access networks like Ethernet, point-to-point links. There's only 2 endpoints in there, so there's no focal point for routing information necessary, okay? So here you see you got your data link frame header, you have your IP packet header, and then inside that is the OSPF packet header, okay? Inside of that is the OSPF packet type specific data. In this case, it's type 1, a hello, okay? And there you see all the fields. Operation. The down state. You got 7 states. There are actually 8 states for OSPF. All right. One state is the attempt state. It's a manually configured state. It's only on non-broadcast, broadcast, multi-access networks. I know that that sounds oxymoronic, but it's, it is what it is. Anyway, the down state is no hello packets received. OSPF is down, not the interface. OSPF is down. The router then sends hello packets, transitions to the init state. Okay, in the init state, hello packets are received from the neighbor. They contain the router ID of the sending router. When you see your own router ID in a hello packet, you transition to two-way state. In two-way state, in this state, communication between the two routers is considered or characterized as bidirectional. On multi-access links like Ethernet, the routers will immediately elect a designated router and a backup designated router. We'll get into that a little later, but the BDR is elected first, and then from the list of available BDRs, the DR is elected, and then a BDR. All other routers go back to being DR others. Now, the way that election works is really like this. Typically, it's a router ID election. You can configure the IP OSPF priority on an interface. Priority can be any value from 0 to 255. The default value is 1, okay? With a default value of 1, it becomes a router ID election for the DR and BDR. If you configure IP OSPF priority 255 on an interface, then that interface, that device, that router should be the DR for that segment. However, if another router has 255, it'll revert to the router ID election. Highest router ID wins, okay? On multi-access. Now, the way the DR-BDR election takes place, first, the protocol looks at all router priorities. Any router that has a priority of 0 can never be the DR or BDR. They are removed from the running. What you have left is an available set of BDRs. Then you look at all of the router IDs and priorities of the BDRs. The highest router ID or priority becomes the DR. The second highest router ID or priority becomes the BDR. All remaining BDRs drop back to being DR others. DR others simply means you're not the DR, you're not the BDR, period. That's it. You're just an OSPF router. Anyway, from there you transition to the EX start state. After EX start on point-to-point networks, two routers decide which router initiates the DBD packet exchange, becomes the master on the link, and decide upon the initial DBD packet sequence number. Then you go from EX start to exchange. Routers begin to exchange database description packets. If additional router information is required, then they transition to the loading state. Otherwise, they transition to full. Once you hit full, the Dijkstra algorithm is run on the link state database, and the best routes are deposited in the IP routing table. In a loading state, link state requests and link state updates are used to gain additional route information. Routes are processed using the shortest path first algorithm. Transition to full. After full, you've calculated the best routes, and you are now depositing routes in the IP routing table. Link state database of the router at this point is fully synchronized. Algorithm run on it, the routing table is populated. To determine if there's an OSPF neighbor on the link, the router sends a hello packet, contains its router ID out all OSPF enabled interfaces. The hello packet is sent to the reserved all SPF router, IPv4 address, multicast address of 224.0.0.5. Can anybody tell me what the layer 2 multicast address would be for that? I'm waiting. Actually, I'm vaping, but I'm waiting for you to answer that. Somebody, anybody, text it. Holler it out. What's the layer 2 multicast address for 224.0.0.5? You sleeping? Who's sleeping? 01005E. 000005. The DR-BDR address is 224.0.0.6. What do you think the layer 2 multicast address is for that one? Yeah, you knew that. If you knew that, you would have hollered it out. Anyway, it's 01005E 000006. That is the layer 2 DR-BDR multicast address. Remember, routers accept frames when they're addressed to the router. If it's not addressed to the router discards the frame. When you enable OSPF on a router, it also enables the layer 2 multicast address to receive those layer 3 packets. Does that make sense? Sure it does. Anyway, somebody knew that, so they say. Anyway, only OSPF v2 routers process the packets. Why? Because 224.0.0.5 is an OSPF v2. It's an IPv4 number. Get it? OSPF v3 has a different number. The OSPF router ID is used by the OSPF process to uniquely identify each router in an OSPF area. Router ID is a 32-bit number formatted like an IPv4 address and assigned to uniquely identify a router among OSPF peers. See, the good thing about that is that, since routers, everything they advertise is tagged with their router ID. If you really know how to read a link state database and a routing table, you can draw a picture of the network, okay? Including the link speeds, the bandwidth. All right, but you really got to know how to read the routing table and the link state database, as well as the neighbor table and your CDP neighbor list. When a neighboring OSPF-enabled router receives a hello packet with a router ID that is not within its neighbor list, the receiving router attempts to establish an adjacency with the initiating router. Process routers used to establish an adjacency on a multi-access network. You go from down to a NIT. When OSPF v2 is enabled on the interface, R1 would transition from down to a NIT, start sending OSPF v2 hellos out the interface in an attempt to discover neighbors. Now realize, OSPF will only send hellos out interfaces that are up and that you have a network statement for in OSPF. If you got 3 interfaces, 192.168.10.24, 20.24, 30.24, if you only add network statements for the 10.24 and the 20.24, no hello packets go out the 30.24 interface because there's no network statement for it indicating OSPF should try to route over that interface. From down to a NIT, at a NIT, when R2 receives a hello from the previously unknown R1, it adds R1's router ID to the neighbor list, responds with a hello packet containing its own router ID. Two-way, R1 receives R2's hello, notices the message contains the R1 router ID in the list. Okay, so since you see your own router ID in the list of neighbors, you immediately start other processes, okay? In the list of R2's neighbors, R1 adds R2's router ID to the neighbor list, transitions to two-way. If R1 and R2 are connected via point-to-point, they immediately transition to EX start. If R1 and R2 are connected over a common Ethernet broadcast network, Ethernet, DR-BDR election occurs. Once you elect the DR, designated router, and BDR, backup designated router, where the router with the highest router ID or highest priority is elected as the DR, the second is the BDR. From there, after two-way, routers transition to database synchronization states. This is a three-step process as follows. Decide the first router. The router with the highest router ID becomes the master on the link and sends its database description packets first. You exchange database description packets, as many as needed to convey the entire database. The other router has to acknowledge each database description packet with the link state acknowledgement packet, LSAC. You send an LSR. Each router compares database description information with the local link state database. If the database description has more current link information, the router transitions to a loading state. After all LSRs have been exchanged and satisfied, routers are considered synchronized and in a full state. Updates, LSUs, link state updates are sent only when a change is perceived. These are incremental, or every 30 minutes to the all SPF address. Okay? Now, the 30-minute update is simply a check to make sure nothing changed. It's a simple acknowledgement, and everybody goes back on their 30-minute timer. No other information other than the tiny little hello packets is exchanged. However, when a change is perceived, the link goes down, an incremental update. All the routers within the area have to recalculate their link state database. Once link state acknowledgements have been set for all the LSRs sent and the LSUs received, then they calculate the algorithm, and then they go on their 30-minute timer again. Multi-access networks create two challenges for OSPF regarding the flooding of link state advertisements. You have the creation of multiple adjacencies. Think about this. Every other OSPF router on that multi-access network has to become fully adjacent with every other OSPF router. That means every router is sending all their information to every other router. That's problematic. On multi-access networks where you have quite a few routers, think about it. Look at the diagram. You got what, 5 routers? But you have 10 adjacencies. Do you get the idea? That's 10 different adjacencies you have to send information to. That's insane. Creation of multiple adjacencies. Ethernet networks could potentially interconnect many OSPF routers over a common link. Creating adjacencies with every single router would lead to an excessive number of LSAs exchanged between routers on the same network. So what happens is you're flooding the network with management information, protocol information. That bandwidth is supposed to be used for user information, not protocol information. Extensive flooding of LSAs. Link state routers flood their LSAs anytime OSPF is initialized or when there's a change in the topology. That flooding can become excessive and bring the network down. An increase in the number of routers on a multi-access network also increases the number of LSAs exchanged between the routers. The flooding of LSAs significantly impacts the OSPF operation. Remember, I told you that on any given network, 50 routers is about the max for OSPF. All right. Now, in a multi-access network where every router is basically directly attached to every other router, they have to send their information to each other, all of them, everybody to everybody all the time. All right. So if you elect a designated router to act as the focal point for all routing information within a given area or on a multi-access network, then only that designated router updates every other router. Everybody sends their stuff to the DR. The DR then determines who gets what. Okay? Anyway, If every router in a multi-access network had to flood and acknowledge all received LSAs to all other routers on the same multi-access network, the network traffic would become quite chaotic. On multi-access networks, OSPF elects a designated router to be the collection and distribution point for all LSAs sent and received. A backup designated router is also elected, just in case the designated router fails. All other routers are DR others, designated router other, DR other. Also, people also call it druther, but it's DR other. All right, simply a router that is not the DR, not the BDR. The DR is only used for the dissemination of LSAs. The router still uses the best next top router indicated in the routing table for the forwarding of other packets. That means not OSPF packets. Get it? So the designated router, while it still routes regular traffic, it does this other function of ensuring all other routers within the multi-access network have full and accurate link state databases. Oh, look at that, we're at the end. So you guys should do that quiz at the end, but let's knock this out. Open shortest path first, OSPF, built off of an earlier version of ISIS. Purely hierarchical link state routing protocol developed as an alternative for RIP. Link state routing protocol uses the concepts of areas for scalability. No more than 50 routers to an area, remember that. A link is an interface on a router. Link is also a network segment that connects two routers, or a stub network, such as an Ethernet LAN connected to a single router with no other neighbors. All link state information includes the network prefix, prefix length, and the cost of the link. Remember, OSPF's metric is cumulative cost, forward path from the router making the decision all the way to the destination node. That means including the link to reach that node. That's also calculated in. All routing protocols use routing protocol messages to exchange route information. The messages help build data structures, which are then processed using a routing algorithm. Routers running OSPF exchange messages to convey routing information using 5 types of packets: hello, database description packet, link state request packet, link state update packet, and the link state acknowledgement packet. For short, they're typically called hello, DBD, DDP, DB, okay? All mean database description packet. LSRs for link state requests, LSUs for link state updates, and LSX for link state acknowledgement. Remember, DBDs, LSRs, LSUs are acknowledged. Hellos are never acknowledged in any protocol. OSPF messages used to create and maintain 3 OSPF databases: the adjacency database, which is the neighbor table, the link state database, which is the topology table, and the forwarding database, which is the routing table. Router builds the topology table using the results of calculations based on the Dijkstra shortest path first algorithm. The SPF algorithm is based on cumulative cost to reach a destination device, not network, device, because you're counting the link to get to that device also. In OSPF, cost is used to determine the best path to the destination. Remember, lowest cost path is always the best path, okay? To maintain routing information, OSPF routers complete a generic link state routing process to reach a state of convergence. First, they establish neighbor adjacencies using hellos. Then they exchange link state advertisements using LSRs, LSUs, database description packets, build the link state database, execute the Dijkstra shortest path first algorithm, choose the best route to every destination. With single area OSPF, any number can be used for the area. The best practice is to use area 0, because area 0 is the transit area, the backbone area, the area that all non-zero areas must attach directly to in order to reach other non-zero areas. Single area OSPF is useful in smaller networks with few routers. Multi-area OSPF, one large routing domain. Large routing domain can be divided into smaller areas to support hierarchical routing. Do realize that when you start dealing with hierarchical protocols, hierarchical addressing is imperative. Routing still occurs between the areas, that's inter-area routing, while many of the processor-intensive routing operations, such as recalculating the database, are kept and maintained solely within an area. OSPF v3 is the OSPF v2 equivalent for exchanging IPv6 prefixes and prefix lengths. Recall in IPv6, the network address is referred to as the prefix. Subnet mask is called the prefix length. OSPF uses the following link state packets, LSPs, to establish and maintain neighbor adjacencies and exchange routing updates. You have type 1 is a hello, type 2, database description packet, type 3, link state request, type 4, link state update, type 5, link state acknowledgement, and exactly how you see them there is how we typically speak of them. DBDs, LSRs, LSUs, LSACs. Link state updates, also used to forward OSPF routing updates, such as link changes. Hello packets are used to discover OSPF neighbors, establish neighbor adjacencies, advertise parameters on which two routers must agree to become neighbors, elect the designated router and backup designated router on multi-access networks like Ethernet. Point-to-point links, however, do not require a DR-BDR, so there's never a DR-BDR election on a point-to-point link. Some important fields in the hello packet are the type of packet, the router ID, the area ID, network mask, hello, interval, router priority, dead interval, DR-BDR, and a list of neighbors. The states OSPF progresses through to reach. Convergence are down, init, two-way, EX start, exchange, loading, full. You must know those 7 states, okay? There's an 8th state. It comes between down and init. It's called attempt. Don't worry about it. You don't need to know it. When OSPF is enabled on an interface, the router has to determine if there's another OSPF neighbor on the link by sending small hello packets that contain the router ID out all OSPF enabled interfaces. What they mean by OSPF enabled interfaces is simply a network statement in your routing protocol for that given network. The hello packet is sent to the reserved all OSPF router IPv4 multicast address of 224.0.0.5, layer 2 multicast address of 01005E 000005. Only OSPF v2 routers process those packets. When a neighboring OSPF enabled router receives a hello packet with a router ID not within its neighbor list, receiving router attempts to establish an adjacency with the initiating router. After the two-way state, routers transition to database synchronization states, which is a 3-step process. Multi-access networks can create 2 challenges for OSPF regarding the flooding of LSAs, creation of multiple adjacencies, as well as the extensive flooding of LSAs to all of those adjacencies. Dramatic increase in the number of routers also dramatically increases the number of LSAs exchanged between the routers. Flooding of LSAs significantly impact the operation of OSPF if every router in a multi-access network had to flood and acknowledge all received link state advertisements to all other routers on the same multi-access network. The network traffic would become quite chaotic and would consume an awful lot of bandwidth. This is why a designated router and a backup designated router election is necessary on a multi-access network. OSPF elects the designated router to be the collection and distribution point for LSA sent and received. A BDR is also elected in case the DR fails. Realize the BDR keeps track of the DR's update activity. When the DR stops updating the network, the multi-access network, the BDR immediately promotes itself to DR, takes over the task of updating the network. A new BDR is elected from the remaining possible BDRs that went back to being DR others, okay? Now, the DR BDR election is typically highest router ID. If you configure the interface priority using the IP OSPF priority command, if you set it to 255, you should be the DR. However, if another router on the same multi-access network has a priority of 255, it will revert to a router ID election. Okay, that's it for that one. Jesus, it's over. Any questions? Hey, talking to you guys, I think you're sleeping. Hello? Hello?
Yes, Chris, actually, can you explain about, I know you did, conversions?
What do you mean convergent?
Right, do you say
Okay.
convergent? Yes, please.
All right, so routers on a network will communicate with other routers running the same routing protocol. Okay? Now, while they're performing that communication, not all network destinations are reachable. However, more become reachable as the router gets more comprehensive information from other routers and calculates it, right? Now, when every router in a routing domain, doesn't matter if it's RIP, doesn't matter if it's CIGRP, doesn't matter if it's OSPF, along with all of its different areas, doesn't matter if it's ISIS. When all routers agree on what the network looks like, they are said to be converged. That means all destinations within that network are reachable.
Okay, thank
Does
you.
that make sense?
That's very clear. And
Okay.
just to clarify on link state, so link state when so it's like a router to router and router to stop network.
Router to any other router that it's running that routing process on. In other words, a link is simply an interface on a router, right?
Right.
Okay. Now, your connection to a host computer is a link, technically, but for our purposes, a link is an interface on a router. When that link is up, that link is available. When that link is down, that link is no longer available. That network is no longer available.
I see.
Now, when that happens, that is known as the link state, its current state.
Okay.
And available, down, unavailable. Routers communicate the state of the links that they know about to each other. Because, you know, the general idea is if you're, let's say you have a really large network, right? You got like 200 routers. You'd really want to cut off a packet. Let's say router 1 is sending a packet all the way over to router 200. Okay? But at some point in that path, it was discovered or actually advertised that the link off of 200 is no longer reachable. Should you carry that traffic all the way to router 200 to drop it at the link? Or should you maybe advertise to other routers that link is no longer reachable and stop packets much sooner so you can conserve routing and transmission resources? So it's the state of the links in the network.
Okay. Thank you.
Make sense?
Oh, thank you. That was
Any
very
other questions?
not as of now.
Okay, so take a 15-minute coffee break.
Break.
Yeah, I know. I saw that in text. All right, take a few minutes. Take 15 minutes. We'll come back. We'll start this other one. The other one has a couple of labs in it. Okay? And I think this afternoon when Kevin gets here, some of you guys got to cough up that hands-on final. Still waiting for 2 groups. Okay?
Yes.
All right, take 15 minutes. 5 more minutes. We're ready, people? Hello, hello, hello. We ready?
Yes, ready.
Time to get together. Back. I see a couple of backs. We good to go. Let's get the next one rolling. Oh, that was 1 and 2. All right, so module 2. I'll just get some of this stuff out of the way. Remember, if you got questions, shout out or text. All right. Single area OSPF, implementing it. should be able to configure an OSPF v2 router ID. Now, once upon a time, we used to allow this to happen by, automated processes, the router. In the absence of the router-ID command and a loopback interface, it'll use the highest active physical interface address as its router ID. Now realize that physical interfaces are prone to physical layer failures, and then the router would attempt to reestablish itself using the next highest active physical interface ID when the highest goes down. And then a short time later, the highest active physical interface comes back up. So you can see that causes stability issues. So nowadays, we hard configure the router ID. We'll get to that. Configure single area OSPF v2 in a point-to-point network. Configure the OSPF interface priority to influence the DR-BDR election in a multi-access network. I will caution you on that. OSPF operates, for the most part, whoever gets there first. So once DR-BDR have been chosen, they stay DR-BDR unless interface of the DR goes down or the process is cleared. So just changing the priority will not change the DR-BDR. You have to take other steps to force the change. Modify single area OSPF v2, implement modifications to change the operation of single area OSPF v2, like interface timers, costs possibly. You have default route propagation. This is where you configure a quad 0 on an edge router, possibly pointed at the internet, or simply another routing protocol. And then you originate that information into OSPF so that routers can build a path all the way up to the gateway of last resort. Verify single area OSPF v2 through various commands. The router ID. This figure shows topology used for configuring OSPF v2 in the module. The routers in the topology have a starting configuration, including interface addresses. There's currently no static routing or dynamic routing configured on any of the interfaces. All interfaces on R1, R2, and R3, except the loopback one on R2, are within the OSPF backbone transit area 0. The ISP router is used as a gateway to the internet of the routing domain, okay? Now realize, just because it's a loopback interface, okay, it can be used as a non-OSPF destination. All right, so if you configure a quad 0 to that loopback interface, that will go into OSPF and set the gateway of last resort to that loopback. OSPF v2 is enabled using the router OSPF process ID global config mode command. Remember, the process ID is any number from 1 to 65535. This is selected by the network administrator. It is locally significant. That means that it is never communicated to any other device, and it does not have to match on neighboring devices. I will tell you, if you have a router like this router, R1, and you type router OSPF 10, and you configure network statements, etc., and then you type router OSPF 5 and configure network statements, you can have some interfaces in process 10, some interfaces in process 5. Some interfaces may be in both processes. However, one process is completely oblivious to the other process. Both processes will maintain separate neighbor tables, separate link state databases. Both processes will contribute to the common IP routing database. In other words, the routing table, okay? Anyway, consider the best practice, however, to use the same process on all OSPF routers so that you know that's one common routing implementation. An OSPF router ID is not an IP address technically. Although it is in IP address form, it's simply a 32-bit value. You can have 0.0.0.1. 0.0.0.2. You can have 1.1.1.1, 1.1.1.2. Okay?
Question. So
Yep.
how does the network admin determine which ID number to use?
Well, you just like make these up. Let me give you a little diagram here to try and, give you a rough idea.
Okay.
But I'm going to pull up the whiteboard. Okay. Supposing I had a router. Remember, OSPF is a hierarchical routing protocol?
Right.
Okay. So I have routers like that, right?
Right.
When you look at it, this router here could be 1.1.1.1. And then over here, this could be let's say subdivision 1 of the network. So this would be let me just get that going. 1.1.1.2. Okay. 1.1.1.3, that is, and then let's say this is 4, should have made that 2, but too late now. And this is 1.1.1.5, okay? Or you could do 1.1.segment2.1, 1.1.3.1, and this one would be 1.1.3.4. You get the idea here. So there are a multitude of different ways to do this. You could even do this. You get the rough idea, right?
Yes. Uh-huh.
So you choose these values, okay? They're important only to you in defining the hierarchy of your network, if that makes sense.
Right. So it depends on an enterprise, like how it is set up?
Right. You would typically try to follow some kind of hierarchical structure so that you know the placement of the given device that you're numbering.
Okay.
Remember, if you really know how to read a link state neighbor table, link state database, routing table, and CDP neighbor table, you can actually draw the picture of the network with all of the link speeds, because that's how much information is contained in link state databases, routing tables, neighbor tables, and CDP tables. You could draw the diagram of the network. So you want to try and number your devices logically. You know what I mean?
Right.
In terms of their position in the hierarchy.
I see.
Okay?
Thank you.
So an OSPF router ID, simply a 32-bit value represented as an IPv4 address in dotted decimal format, used to uniquely identify a single OSPF router. Router IDs must be unique. All OSPF packets include the router ID of the originating router. So like, let's say you're 10 routers away and you receive a route for a network statement on router 1, okay? You will be able to see router 1's router ID in that link state database because router 1 is the one that originated that route. Does that make sense? It'll allow you to see exactly where specific networks came from, which router originated it. All right? Every router requires a router ID to participate in an OSPF domain. Routing domain is what it's called. Can be identified, defined by an administrator, or automatically assigned by the router. The router ID is used by an OSPF-enabled router to do the following: participate in the synchronization of OSPF databases during the exchange state. Router with the highest router ID will send their database descriptor packets first. They are the master on the link. Participate in the election of the designated router. In a multi-access LAN environment, the router with the highest router ID is elected the designated router. The routing device with the second highest router ID is elected the backup designated router, although the IP OSPF priority is the preferred way of defining DR, BDR on multi-access networks. Cisco routers derive the router ID based on one of three criteria in the following preferential order. If you go into OSPF, router OSPF process 10, and you type router-ID, and then give it a value, 1.1.1.1. This is the recommended method to assign the router ID, okay? Since we now use IPv6, OSPF v3, we always do it this way, okay? We used to do it by using loopbacks. Originally, when OSPF first came out, it was the highest active physical interface. Things change over time because you want to build stability into the protocol, all right? Do note that the router ID is absolutely not a routed value. That means you will never have a network statement for your router ID, okay? The router chooses the highest IPv4 address of any configured loopback interface. So in the absence of the router ID command, if there is a loopback interface, it'll be the highest loopback interface IP address. In the absence of both the router ID and or the loopback interface configured, then the router simply chooses the highest IPv4 address of any active physical interface. Interfaces that are shut down are not considered, okay? So let's say you have a loopback interface on a router and you use the router ID command. Once you clear the process, it will be the router ID value, regardless of the loopback, all right? If you have a physical interface and you configure a loopback interface, when you clear the process, it will be the loopback interface. If you have a physical interface that has a high IP address and you put like 1.1.1.1 on the router ID command, when you clear the process, it will absolutely be the router ID command. So that's the preferred method by the protocol. In the absence of the router ID command, it'll use a loopback address, the highest value, okay? That is active. In the absence of that, it simply uses the highest active physical interface IP address as its router ID. Instead of relying on the physical interface, the router ID can be assigned to a loopback interface. Typically, the address for this type of loopback interface should be configured with a 32-bit subnet mask. Why? Because you're not routing this. It's a simple host route. An interface value, a 32-bit host route, would not get advertised as a route to other OSPF routers. OSPF does not need to be enabled on an interface for that interface to be chosen as the router ID. That's independent of the routing process. It's just looking for the highest value on the device. In our reference topology, the router ID for each router is assigned as follows. Router R1 uses 1.1.1.1. So you type router OSPF process 10, router-ID 1.1.1.1. Show IP protocol, pipe include router ID, and you'll see that the router ID is 1.1.1.1. Now do note, if you ever try to start up OSPF, let's say you type router OSPF 10 and press enter. If you have no active interfaces with IPv4 addresses, no loopback interfaces, and you don't have the router ID command, the protocol will shut right back down. It'll say no router ID, terminating process, okay? Anyway, use the router ID, give it a router ID, config command to manually assign the router ID. In the example, the router ID 1.1.1.1 was assigned to R1. show IP protocol command to verify the router ID. After a router selects a router ID, an active OSPF router does not allow the router ID to be changed until the router is reloaded or the OSPF process is reset. Clearing the OSPF process is the preferred method to reset the router ID. The reason for that is because different devices, if you go reloading multiple routers, they all reload at a different speed. And OSPF does really operate first come, first serve. All right, so clearing the process is the best way. All right, so this is the entire command for it. Okay. Clear the IP OSPF process. Any adjacencies will be reset, and you'll see your new router ID. Point-to-point OSPF, you can specify interfaces that belong to a point-to-point link by configuring the network command. You can also configure OSPF directly on the interface with the IP OSPF process ID, area, whatever area command. Basic syntax for the network command is in the protocol, router OSPF 10, network, whatever the network subnetwork address is, the wildcard mask appropriate for that network or subnetwork, area, and whatever area you want that interface network to be in. The network address, wildcard mask syntax used to enable OSPF on interfaces. Any interfaces on a router that match this part of the command are enabled to send and receive OSPF packets. Okay. Now remember, when you use the network address there in the wildcard mask, the alternatives are the interface address and a quad 0 wildcard mask. Okay. Anyway, when configuring single area OSPF v2, the network command has to be configured with the same area ID value on all routers. Although any area ID can be used, it's a good practice to use an area ID of 0 with single area OSPF v2. This makes it easier on you if you ever later decide to migrate to multi-area OSPF, because you can keep the routers that are already in area 0 that will stay in area 0 with their config, and then just modify the other routers with their area IDs. Wildcard mask, typically the inverse of the subnet mask. The easiest method for calculating the wildcard mask is to simply subtract it from a full-on 32-bit mask of 255.255.255.255. Okay? Now, if you had a subnet mask of 255, the first diagram for the 24 bits, actually both of those diagrams are wrong, so let me explain that to you. If you have a /24, it equals 255.255.255.0. Okay? Now, if you take the mask of what you would get as a result is simply okay. Now, if you had a /27, that would equal, and if you were to subtract it from, oops, you would end up with a result of does that make sense? Come on, what's going on with this damn laptop? Does that make sense?
Yeah.
Simply the inverted form of the subnet mask. If you had 24 bits on, well, 24 bits are off and then 8 bits are on. Okay? All right, so it's simply the inverse of the wildcard mask. Within routing config mode, 2 ways to identify the interface that will participate in the OSPF process. Okay? In the first example, wildcard mask identifies the interface based on the network addresses. Any active interface configured with an IPv4 address belonging to that network will participate in the OSPF v2 routing process. Now, do realize, if you did that 10.10.1.0.0.0.255, if it was actually 10.10.1.0 with a /25 and 10.10.1.128 with a /25, both of those interfaces would be routed because they're contained under this 10.10.1.0.0.0.255. Does that make sense? I hope. If you had 2 subnets, let's say you took this and you cut it into 10.10/25, 10.1.128/25, 2 networks on 2 different interfaces on this router. You could list both of them with this one statement. However, you should not do that. You should do them as separate entries so that it is clear both interfaces were actually intended to be routed in this process. Now, another way you could do it is you could put the interface address and a 0.0.0.0 mask, okay? Some iOS versions allow the subnet mask to be entered instead of the wildcard mask. The iOS converts the subnet mask to wildcard mask format, okay? As an alternative, OSPF v2 can be enabled by specifying the exact interface IPv4 address and using a quad 0 wildcard mask. If you look in the diagram, you have network 10.10.1.1. That's the interface address. And then 0.0.0.0.0, 0.0.0.0, yeah, I had it right, to indicate that specific interface, okay? Now, that will route the entire network on that interface, but it specifies to start the process on that interface. The advantage of specifying the interface is that the wildcard mask calculation not necessary. Note, in all cases, the area argument specifies area 0. So this would be single area OSPF. Configure OSPF directly on the interface. You can use the IP OSPF process ID 10 area 0 command. Now, if you do that, you don't need network statements. Do note, if you're on router 1 and you had it configured like this, on the other end, let's say router 2, you could configure it like it is on the bottom, IP OSPF 10 area 0. OSPF doesn't care. You enabled it on the interface. That's the same as having a network statement for it. All right? So one router could be configured with the IP OSPF 10 area 0 command, and the other end of the wire be configured with the IP address or the wildcard mask method. Okay? They all work interactively, interchangeably, I should say. Okay? And then in this case, you would simply remove the network statements, but do note you should have the router-ID command in there and the auto command, auto cost reference bandwidth command if you have interfaces that are higher speed than 100 megabit, as well as anything that affects the protocol as a whole would be done in the protocol, like default originate, auto cost reference bandwidth 1000 for gigabit interfaces. All right, passive interface. Now, whenever you type a network statement like this, what it does is it allows OSPF to send hello messages out that interface. And more importantly, it allows the protocol to take that network and send it out other interfaces to other routers so they know how to reach it. Okay? Now, passive interfaces, LAN segments. Okay? A LAN segment where all you have are host computers or peripheral devices, and there are no other routers on that link. You don't want to transmit hello packets out that interface. First of all, it's a waste of processing to generate the hello, a waste of line time to transmit it, and it's a security risk because somebody could sniff it. All right? So by default, OSPF messages are forwarded out all OSPF-enabled interfaces. However, the messages only need to be sent out interfaces connecting to other OSPF-enabled routers. Sending out unneeded messages on a LAN affects the network in three ways: inefficient use of bandwidth. Available bandwidth is consumed transporting unnecessary hello packets. Inefficient use of resources. All devices on the LAN now have to process and eventually discard that message because it's not for them. Increased security risk. Without additional OSPF security configurations like authentication, the OSPF messages can be intercepted with packet sniffing software. Routing updates can be modified and sent back to the router using a packet generator, thereby corrupting the routing table with false metrics and networks that misdirect traffic. Okay? So it's bandwidth, resources, and security. Passive router configuration mode command to prevent transmission of a routing message through a router interface, but still allow the network to be advertised to other routers. Show IP protocols command, then used to verify that the interface is listed as passive. So in this case, they put the loop back in. Why? Because in this particular diagram way back at the beginning, the loopback is connected to what's supposed to be the internet. You wouldn't route out to the internet using an IGP. Do note that you would also put this command on every LAN interface where there are host computers. If there are no routers to receive OSPF, it should be listed as passive. All right. By default, Cisco routers elect a designated router and backup designated router on Ethernet interfaces, even if there's only one other device on the link. You can verify this using the show IP OSPF interface command. DR-BDR election process is unnecessary as there can only be two routers on a point-to-point network between R1 and R2 if you refer to the diagram at the beginning. Also notice in the output that the router is designated the router network, designated the network type as broadcast. So when you type show IP OSPF interface G00, all right, the network type is broadcast because it's Ethernet. If it was serial, it would be point-to-point. The cost is 1 because it's gigabit, okay? The designated router is a router ID of 2.2.2.2 with an interface address of 10.1.1.6. Note ours is 10.1.1.5, okay? Then the backup designated router with a router ID of 1.1.1.1. You see our router ID is 1.1.1.1. And our interface address is 10.1.1.5. Okay? So the designated router is router 2. We are the backup designated router on that link. The hello and dead interval is 10 by 40. The dead interval is 4 times the hello value. Okay? By default, those are 10 by 40. To change it to a point-to-point network, you go to the interface and type IP OSPF network point-to-point on both ends of the link. Okay, you can't do it on one. The network type has to match on the other end of the link. Okay, so now once you set it to IP OSPF network point to point, you're going to see an adjacency change. Okay, and then it's going to come up. The network type will be point to point. OSPF will stabilize. Okay. Use loopbacks to provide additional interfaces for a variety of purposes. By default, loopback interfaces are advertised as /32 host routes, regardless of the mask on the interface. To simulate a real LAN, the loopback in can be configured as point-to-point network to advertise the full network. This is what R2 sees when R1 advertises the loopback interface as is, no additional config. It shows as an O, intra-area, but it shows the interface address /32. Now, if you go into R1 and you go to the loopback interface, type IP OSPF network point-to-point. Then go back to R2 and type show IP route. And now you see intra-area route, but it's the subnet with the subnet mask that was applied to that interface. Via the next hop address, learned about it 3 minutes, 5 seconds ago, out gig 000. OSPF's administrative distance is 110. The cost to reach that link is 2. Packet tracer, what time is it?
Almost lunchtime.
It's almost lunchtime, but you guys can work through lunch, right? You know, grab your food at your computer. I know you won't mess up your keyboards. Why don't you work this packet tracer? Kevin should be here shortly.
I'm right here, man.
Oh, you there? Oh, I didn't see you, man. You were like way down in the list. I got a screen shared. I can only see a couple of pictures at a time.
Oh yeah, I know what you mean. You got like 5, 6 at best.
Yeah, and I don't scroll back and forth because then I end up muting stuff.
Yeah.
Anyway, it's 11:45. Why don't you take a look at this packet tracer? And we'll pick this up after lunch, okay? Is everybody okay with that? These guys don't answer. Do they answer you, Kevin? Because they never answer me. It's rare.
Oh, yeah.
I got to stand here for 5 minutes saying, do you hear me? Is anybody there? Hello?
Now they're starting to pick up. They're in chat. There we go. All
Hello?
of them are answering. They're like, yeah.
All right, so take 15 minutes. Take a look at this packet tracer. It shouldn't be too tough to do. All right? If you're going to do it, you could probably do it in your spare time while you're sucking down some food for lunch. All right?
This is all shit you guys have done before.
Right? I know. That's why it should be like 1, 2, 3.
I even told you guys about passive interfaces since the Sem 1 project, so y'all are good.
Right? All right. So take a few minutes, look at this. I'll come back to you at 12, break you for lunch, and then we'll pick up after that. I know 2 groups owe us the hands-on final, Kevin. 2 groups got it in. I think
Okay.
2 and group 4 got it in. I think it's group 1 and group 3 that got to give it up.
All right, fair. After you're done with your presentation, we'll take them out for that.
There you go.
How many more slides do you have left?
Let me see. I got to break it. This is, oh my God. We're only up to 22 of 77.
Oh, shit. Ha!
Yeah, but this is module 2.
Ah, okay.
All right, this is module 2, and there are a couple of packet traces in here. So we already did module 1 this morning, then we went right into this one.
What was module 1 then?
OSPF, but this is configuration.
Ah, okay.
That was about OSPF. This is configuration.
Gotcha.
In worst case scenario, we could always finish this tomorrow.
Yeah. Well, you decide when you want to
We'll
cut them
figure
a
it
break. Yeah.
Yeah, we'll figure it out. But now just look at the packet tracer, work it, and then we'll come back at 12 o'clock. I'll break you for lunch. We'll figure out after lunch what we're going to do. All right?
Have fun with Packet Tracer, everybody.
See yous. Going on mute.